Hey, AP Chemsters, this is Mrs. Vanderwally bringing you part 2 of chapter 1.3, and they're going to continue on and finish off 1.4. So I left you with 1.3 saying, copy this down. So let's kind of quickly talk about this before going on. So we can say, all things that have mass and take up space, that's your definition of matter. And they ask, is it variable composition? What does that mean? Does the composition change? So a pure substance, no, will not change. It will always be H2O, 2 hydrogens with 1 oxygen, or it won't be water. On the other side over here, think about my sweet tea idea of a mixture. Remember, it's sugar and water and, tea stuff. And can I put 1 teaspoon of sugar in there? Sure. What if I like it sweeter? Can I put 5 teaspoons of sugar in it? Sure. And so that's what we mean by variable composition. You can change the amount of sugar to tea stuff, okay? And that would be then a mixture. Then if you go back and look at the pure stuff, oops, something just happened. Then what's happening here, we can have separate into simpler substances. If the answer is no, it's an element. So if it's helium, it can only be helium, just like in the Goodyear blimp. Okay, if you can separate it into simpler substances, then it's a compound like water. Remember what I said earlier? If you put electrolysis through pure water, you're going to break it up into hydrogen and oxygen. So you can break it down. Over here, it's talking about mixtures. Again, hetero means not the same throughout. And they're talking about wet sand. I probably wouldn't have used that. I may have used like chicken noodle soup for their example, but hey, I'm not the publisher here. But so wet sand, if you look at the microscopic picture, you'll see that the water and the sand are collected at the bottom and the water is on the top. You see distinct layers. You can see a demarcation line. This is where the water is. This is where the sand is. That's heterogeneous mixture. And then homogeneous is tea with sugar. Can you see the sugar clumps? No, you can't. But on a microscopic viewpoint, you can see here's a sugar, here's a sugar, here's a sugar. And it's pretty well mixed throughout. You see the water surrounding the sugar. That's what allows it to dissolve. We'll talk about that a little bit later in the year. But anyway, but as looking at the big picture, I can't see the distinguishing parts. But if you look at the microscopic picture, I see the sugar and the water still. Okay, so hopefully that helps. Let's go on to the next page. So problem number 3, why don't you read this, pause this, figure out what you're going to do, and have this problem 3 completed before you come back, all right? And then we'll talk about it. All right, welcome back. Well, hopefully you know something about styrofoam, copper, and iron. How would I do this? I would probably stick some water in it. Why would I do that? Because styrofoam floats. And then you can use your fingers or some tweezers or something, and you can skim off the styrofoam at the top, drain off the water, and now you're left with copper and iron. Now you might do a melting point and see which one melts off first. That wouldn't be a lot of fun, but you could do that, by the way. I personally would use a magnet. Iron is magnetic, copper is not. I just stick a magnet there, let all the iron particles collect on the magnet, pull it out, you have copper behind. And if you have an electromagnet, then you just turn off the switch and all the iron filings will fall off anyway, and now you have separated. Now it says after separation, are the components pure substances? I'm guessing most of you might say yes here, but the answer is no. Your styrofoam, as we know it, is a mixture of polystyrene and air, okay? And by just putting it in water, you have not taken the air out of the polystyrene to make styrofoam. So the answer to that is no. Styrofoam is still a mixture of polystyrene and air. Your copper and your iron are still pure substances. They're pure elements. So it says after separation, are the components all elements? The answer is no. Iron and copper are. Styrofoam is still a mixture. If you want to drive the air out, then styrofoam would be a compound of polystyrene. Maybe a little bit tricky, maybe not. The next question is dealing with paper chromatography. We're actually going to be doing this tomorrow, hopefully, And but if you are not familiar with what paper chromatography is, may I recommend going on YouTube and just take a look at what some paper chromatography is all about. I really would. If you don't know what I'm talking about, go on YouTube. You can look it up. So the key part here is you're given a beaker filled with black liquid. All right. Then you perform this paper chromatography. So what they've done is put a little dot on there, put that on a strip of paper, you put the paper in some water, let the water travel up. Okay. So go ahead and, if you need to do some research, go ahead and do some research, but go ahead and describe your results for the next two. Pause this and come back. All right, hopefully you're back. If it's a pure substance, all you'll see is a big black smear, okay? And you don't see anything coming out. So that would be your results if it's pure. If it is a mixture, then you're going to see a smear of different colors coming out, like, blues and reds and greens and yellows, all right? And that way it's a mixture of blue ink and red ink and green ink or whatever, okay? So if the black liquid were a mixture, is it homogeneous or heterogeneous? Well, if it just looks black to your eye, then it's a homogeneous mixture. You can't see the different parts out of it. So I'm thinking of, let's say, an overhead marker, which is probably now showing my age. Hopefully you know what an overhead marker is. It looks like a black marker to me, all right, or a Crayola marker. We can do that one too. If it is a mixture, it still looks uniform throughout. It is going to be homogeneous, okay? I would like you to do problem number 5 for homework, and we will discuss this tomorrow. So, pause this, draw this thing out, and we will start the day off doing problem number 5, okay? Let's go on to the next section. Okay, so we are talking about physical and chemical changes and physical and chemical properties. So a change, first of all, it must be accompanied by energy. You need to have energy to have a change, okay? So a physical change is where atoms or molecules that compose a substance do not change their identity. So pause this, come up with some ideas of what a physical change might be and see how you do. All right, did you come up with some? Well, I'm thinking of, some of the easy ones like boiling. I can boil some water. So that's H2O in the pot, it's H2O in the air, it's just changing locations. All right, how about another one? How about an ice cube? Is H2O as a solid? It is H2O as a liquid. How about another one? I have another one. How about dissolving? Oh, that's something for you. So if I put sugar in water, is it still sugar? The answer is yes. Okay, it is still sugar. But like we saw in the picture of that matter chart, it's just in a smaller chunk, isn't it? It's now being surrounded by water. But is it still C12H22O11? The answer is yes, it is. It has not changed its identity. It's changed its location. And finally, here's another one. I said, like cutting a piece of paper. Is it still paper? Yes. All right, its identity hasn't changed, you just separate into smaller pieces. All right, now it says draw a molecular representation of water boiling, okay? So here's my water. I try to have it fill the container, sort of, all right? And they're kind of close to each other, and you notice it's still 2 little small circles are my hydrogens, and the big circle is still my oxygen, okay? Now what? What's going to happen to this, okay? If it's going to boil, are those little Mickey Mouse ears going to fall off? And the answer is no. All right, they stay put. Here we go. So that's my water boiling. It's still H2O. It's still 2 hydrogens and 1 oxygen. I've just changed its location, okay? So what's the difference between physical and chemical? Well, if physical does not change the identity, well, guess what? Chemical does, okay? So what are some examples of chemical changes? Did you come up with a list yet? Well, maybe you have. The first one I think of is burning, because everyone always want to ask if they're in a chemistry class, are we going to blow anything up? Well, what does that mean? We're going to burn something, all right? Have you changed the composition if you burned it? If you burn a piece of paper, is that still paper? And the answer is no. You've changed it. It's now ash. You know, the properties are different. You have a new substance. All right. Another one pretty common is rusting. Not just iron rust, other things can rust too, but what's happening is reacting with oxygen, okay? How about if you have an upset tummy, take some Tums, your plop, plop, fizz, fizz, what's it doing? It's neutralizing, all right? So that stomach acid is no longer stomach acid, okay? It's been neutralized, you make something new. So it says, draw a molecular representation of iron rusting, okay? Well, I need some iron. So how's that? Does that look like a solid to you? All right, I have solid pieces put together, looks like a solid to me. All right, what about over here? Here's my oxygen, and it's supposed to be a gas, okay? And what's happened? I'm going to make some FeO, so here we go. If you want to be specific, rust, as we think of rust, is actually Fe2O3, but for simplicity's sake, I made it FeO. FeO does exist, by the way, but it's not your traditional rust. Okay, so how did I do this? Great question. Well, it looks to me like I broke some bonds and formed new ones. Don't you see that? I split these four apart. I broke bonds. I split these two apart and I made new bonds, all right? That is a chemical thing. So it says, using your two representations, compare and contrast physical and chemical changes. Well, watch this. This is a physical change. Look what I'm doing to my iron. I am flattening out my iron, all right, to now it's a little thin sheet. That's a physical change. Is it still the same iron? Yes, all right. What can I do to oxygen? Can I move it away? Maybe increase its temperature, make them further apart? Yes, I can do that. Those are physical changes that I just showed you, flattening out the iron and making the molecules further apart. That's physical. Did I break any bonds? No, all right. Did I change its representation? Not at all, okay? So what would I write here? Physical are no bonds broken, and chemical are new bonds. Bonds are broken and new bonds are formed, okay? So what's a property? A property is a substance that displays, or a physical one, that displays like changing its composition, all right? A chemical property is one that displays only by changing its composition. Let me show you an example of properties. All right, so this is an example out of what's called the CRC, the Handbook for Chemistry and Physics. You can look up any number about any element, any compound you want, all right? So for example, here's density, the triple point. By the way, the triple point is the temperature and pressure for the solid, liquid, and gas to coexist. Melting point, boiling point, critical point, ionization, and the list goes on and on. These are properties, okay? So actually, most of these are physical. This last one is actually a chemical property, the ionization, because in order to determine this ionization, you are going to change the structure. You're pulling an electron off. You're changing its identity, going from an atom to an ion, okay? So let's go back here again. So what were some physical properties? What were some that I listed on there? Well, let's go back. So physical could be density, a melting point, boiling point, critical point, triple point. Color could be a physical property, all right? I am observing them without changing their identity, okay? What would be some examples of, oops, wrong one. Let me go back. What would be an example of a chemical property? Well, the ionization, which you may or may not know. How about the ability to rust, the ability to react, the ability to burn? Those would be chemical properties, okay? Well, let me throw one back up here just for you know. Physical will also be solubility. We can give a number to its solubility and you are not changing its identity, okay? What I'd like you to do to finish this off is please do Roman numeral 3, problem number 6, and problem number 7 for your rest of your assignment tonight, okay? So please finish up through the bottom of this page for your homework. And once again, I'll leave you with this thought: don't wait to be great. See you tomorrow.